So why don't we start? We're continuing our discussion on vector spaces, and I have a couple here to figure out if they're vector spaces. So why don't we just start with the first one, A. So we have our set as integers, and our field is the real numbers, and our binary operation is just normal addition, and our scalar multiplication is defined this way. Or we have, if I do a real number times an integer, I'm calling that multiplication by just round up the number to the closest integer and then multiply. Does that make sense? Like that's how I'm defining scalar multiplication. So for example, if I had 1.2 times 3, what would that equal? This is integers. Well, remember, the scalar multiplication is the number times the integer is first round up the number and then multiply to the integer. So yeah, it would be 4, right? Or not 4, but 6, right? So this is equal to round up 1.2, which is 2, and then multiply by 3, which is 6. So we're rounding up before multiplication. Do we see that? Okay. So this is addition, and the scalar multiplication is round up. Okay, so let's go through the axioms. Well, first of all, if you see, can anybody see right away if one of these axioms fails? But I think this one is hard to see which fails. But so why don't we just go through all of them and see if it works? So the binary operation is Z with normal addition. Okay, so can someone tell me if that's closed operation? Is normal addition a closed operation on integers? Yes. And why? It's because an integer plus an integer is an integer. Shouldn't have to say this, but is it commutative and associative? Yes. Right? Normal addition is very nice. What is the identity element in addition? 0. And what are the inverses of numbers, of integers for addition? Negative, good. So inverse of Z is negative Z. Someone say, why is it not 1 over Z? Why is it negative Z? Correct, because this is talking about addition, right? Let's talk about multiplication, then that might be a different story. Okay, so let's go through scalar multiplication. Is scalar multiplication closed? This scalar multiplication. First of all, can you say, if it was normal scalar multiplication, would it be closed? So I just multiplied the numbers without doing anything special? No, yeah. Can you give an example of when it's not true? This is for normal scalar multiplication. What's an example of a scalar times an integer that's not an integer? 0 is an integer, that's fine. Remember, integers are like whole numbers along with negatives. Sure. So this is a special type of scalar multiplication, but I'm asking in normal scalar multiplication, so that means I just multiply the two numbers. Yeah, it's, well, not any number that's not an integer. I'll give you an example of when that's not true. You can't just do one number, right? You have to do a product of two numbers. Right, it's always, it's a scalar times an integer. So why is it not just any real number? Because you could do like 1/2 times 2, right? That's fine. That's an integer. So when you do a counter example, you want to do a specific one, right? So you could do like a radical 2 times 2, right? That's not an integer, right? This is a real number, and it's not an integer. And this is an integer. But the product is not an integer. Okay. So does that make sense? So with normal scalar multiplication, integers are not closed. Because when you multiply by a real number, it's not necessarily going to be that you get an integer back. However, we're working with a different scalar multiplication. This is if you have give me any number, but before you multiply by the integer, you want to round up. So now is that closed? The ceiling, yeah, it is closed, right? Because this roundup will always give you an integer, right? Is always an integer, and integer times integer is an integer. Integer times integer equals integer. Okay. So why don't we do some of the easy ones? Yeah, square root 2, I don't know, what is square root 2? Like 1 point something, right? So that would round up to 2. Yes, that would be an example. So square root 2 times 2 in this world would equal round up square root 2, ceiling square root 2, which is 2 times 2, which is equal to 4. Okay. Let's do some of the easy ones. Is it identity preserving? So what is the identity in real numbers, in our field, real numbers? By identity, we mean multiplicative identity. 1, yeah. So is that preserved in scalar multiplication? Yes. So 1 round up is equal to 1. And 1 round up integer is equal to integer. So that's good. All right. Okay, so now let's kind of go through, these are kind of the harder ones. So let's treat them separately. Okay, distributive. This one's not as bad. Distributive and vectors. Okay, so what does that mean? If I have alpha with v plus w, what should this equal? You can say a instead of alpha if you want. For easy, if you want to type it. Yeah, av plus aw. av plus a w. So what is alpha again? Or what does the multiplication do again? So if I want to, so we don't know if this is true, right? What does this do? So look, now we're using the definition of our scalar multiplication, which we defined above. So what is it? Yeah, ceiling and then multiply by v plus w. So now we have, well, I guess we could say, let's say n and m because these are integers. Okay, so now what can we do? Can we distribute it now? Yeah, right now this is normal multiplication, right? So now this is ceiling alpha times n, normal multiplication, plus ceiling alpha times n. Okay, now let's look at the other side. What is alpha circle m? When does the ceiling happen? Whenever you see the circle, right? So we see the circle. So now we put the ceiling. Right, so we see the circle, so then now we put the ceiling. So that's good. So these are the same. So that means it is distributive in vectors. Did everyone follow that? So maybe this is reminiscent of something you did like in pre-calc when you did like verifying identities, right? You have two things that a trig usually these are trig things that were said to be true, and you had to like manipulate one to get to the other. This is kind of in the same realm, right? You have two statements. You have alpha circle n plus n, m n plus n, and you have alpha circle n plus alpha circle n. So you want to fiddle around with both sides or turn one into the other. But sometimes you can't do that, right? That would imply that this is not a vector space. Okay, so now let's go to distributive and scalars and see if that's true. So that would be like alpha plus beta. Oops. Circle n is, what would this need to equal if this was distributive in scalars? And you can use A and B if you want for typing. A n plus B, yeah. And these are circles, right? A circle n plus B circle n. Okay, so let's start over here. What does this turn into? So what does the scalar multiplication do in this world? Does it do that? We don't know, right? We want it to be that, but it may not do that. We don't know if this is true, right? So just based on the thing alone, right? Ceiling of the sum, circle n. So now that's the big question. Is ceiling distributive? Is that true? Is the ceiling function distributive? No, yeah. Can you give an example when it's not distributive? So give an example of two numbers, and first you take their sum and then seal, and then do it separately and then seal. Sure, let's try that one. So let's do 1.1 plus 1.1 seal. And let's do 1.1 seal plus 1.1 seal. Okay, so what is this? This is 2.2 seal. And what is the seal of 1.1? 2. Yeah, so this is 3. This is 2 plus 2 is 4. So we found a counterexample. And what would the n be? This would be like circle. So you could make it like 1.1 plus 1.1, or how do you do it in this notation? You circle like 1 is not equal to 1.1 circle 1 plus 1.1 circle 1. Okay, good. While we're at it, I mean, it's also, I won't go through too much, but it's also not compatible. So let's just make sure we know what compatible means. Compatible. So right now we can just say it's not a vector space, right? Once one of the axioms is false, then it all falls apart, right? So if you can see, if you have like the foresight to see which one would fail, then I would hone in right on that. And you don't have to do what we just did and go through every other one until we get a fail. But if you don't see right away which is the failure, then go through all of them until you get a failure. But let's just see compatible. Let's just remind ourselves what compatible means. It kind of looks like associative, right? So if I have a product in scalar world and then or in field world, and I scale and multiply by n, it should be the same as multiplying them separately. Okay, can someone think of an example where you can think of a pair of numbers where it's not scalar compatible? So meaning, is the ceiling of AB equal to the ceiling of A times the ceiling of B? Can you think of a pair of numbers? Like, so like use 1. It's probably a good starting point, right? Use like 1. So that was a good example where the sum is not, ceiling distributive, but it's kind of like distributive, but like with multiplication, right? Yeah, can you think of a pair of numbers or it doesn't work? My hint is think about negative numbers. Yeah, that's actually a great one. Yeah. So if alpha is equal to -1 and beta is equal to -1, oh, actually that would be fine, right? Because it would be 1 either way, right? But they both round up to -1. Right? Do you see that? Okay, let's try that one. 1.2, 1.2. What's 1.2 times 1.2? 1.44. Okay, alpha beta to the 1.44. So these respectively round up to 4, and then alpha beta rounds up to 2. Good. So it's not compatible. So one I was thinking of was like -0.5 versus like 10 versus and then what is that? This is -2, right? That's the product. So this rounds up to 0. Oh, does 1.1 also work? Take the product, it's somewhere in below. Yeah, yeah, that also works. Yeah, the product is somewhere in between 1 and 2, but they both respectively seal to 2. Yeah, that's good. Okay, so yeah, so we didn't have to do the second part since we already did the show is not distributive. But good. So everyone see like kind of the method. So maybe we didn't see right away that wasn't distributive. So we're going through all the properties, and once something fails, we can just then it doesn't work. Okay, so let's do the next one. So this is a note. real numbers with normal addition and the scalar multiplication is absolute value. Yeah, it's like bingo. Yeah. So real numbers, addition, and we have absolute value. Okay, can anyone see right away which one fails if one of them fails? So the only different part of this is the scalar multiplication. So that's kind of a good hint of where you should kind of hone your focus. Yeah, like so multiplying two numbers. So here's an example. So -2 circle x, or yeah, circle x is equal to absolute value of 2x is equal to 2x. So that's what the function does, the scalar multiplication. So do you have an idea of what fails? So what do you know about absolute value? Yeah, the -2 becomes a 2, and positive numbers stay the same. Yeah, good. It's distribution is the one that fails again. So alpha plus beta times x is not equal to alpha x plus beta x. Good. And can you give a pair of examples? Pair of alpha beta that doesn't work? So when everything of the absolute value is like, yeah, so first of all, let's say this is alpha plus beta times x, good, like 5 and -5 is not equal to alpha x plus beta x. Yeah, since you know about something that's true about absolute value, this is just general truth. General truth is that absolute value is not equal to just splitting it up, but it's actually it gets bigger when you split it up. In some cases, it never shrinks, but yeah. So whenever you use like one negative and one positive, that's always a good example. So you can do -5 and 5. That's good. -5 plus 5x is certainly not equal to absolute value of -5x plus absolute value of 5x, because so what is this? What does that turn into? 0. And then what is this? The right hand side. Yeah, absolute value of -5 is 5, and absolute value of 5 is 5. So it's equal to 10x. Right. So obviously there's some x values where 10x is not equal to 0. Okay. So we just saw one that didn't work, so we don't have to do anything else. Okay. Questions on that one? This is just B, right? All right, let's do the next one. So real numbers, field is real numbers, usual scale of multiplication. But here the addition is different, where the sum of two numbers is just take the smaller of the two. Oh, so the addition is like x plus y, it just is the smaller of the two. And normal scalar. All right. Can anyone see if an axiom fails? Let me bring this over. Yeah, so does anyone have like an idea of which might fail, or should we just go through all of them? Well, first of all, does anyone understand the minimum function? Okay, no, okay. So what does the minimum function do? So give me two random numbers, 2 and 3. So 2 plus 3 is equal to the minimum of 2 and 3. And which is the smaller of the two? It's 2. And yeah, Samantha, inverses is something that is questionable. So whenever you first look at inverses, you always have to think about identity, right? Because inverses are really dependent on what the identity is, right? So what's identity? So sorry, this is not block sum. It's just a symbol. Just a symbol. Yeah, so what does identity mean? Identity means is, let's do what should we call the letter E? Let's say E plus X is equal to, or Y is equal to Y, or X plus E is equal to X itself. So what an inverse is exactly, it's for every single possible X and Y. So you can't have an inverse for every single number, but it's one inverse for all numbers. That's the idea. Identity fails, yeah. Can you explain why? Oh, commutative is fine, right? The minimum between Y and X is the same as the minimum between X and Y, right? You're just looking at the list and picking the smallest. Associative we find too, right? Having 3 numbers and honing in on the smallest is just the same as taking every pair and honing on the smallest, right? Yeah, so let's think about, so let's say precisely what identity fails. So since 2 plus 3 is 2, you might think, so 3 kind of acts like an identity, right? It's a number where if you add it to 2, it lands back at 2, right? Can you think of another number that does that? 2 plus what other number gives you 2 as well? Yeah, n greater than 2. So remember, when I'm saying plus, I mean this weird plus, right? Not normal plus. Good, yeah. So in fact, 2 plus n greater than 2 is also equal to 2. Or equal to, that's fine, right? The minimum of 2 and 2 is 2, because they're both 2. So the idea is you always get this identity if the number is bigger than your original number. So does that make sense? So if I have like x plus what would give me x back? What would need to be in the second coordinate to give you x back? Yeah, any number that's bigger than or equal to x. Yeah, so maybe not x less than x, but how about some other number y that's greater than or equal to x? Not x minus 1, right? X minus 1 would just spit out x minus 1 because it takes the minimum of the 2 numbers. So is this making sense? Yeah, x plus 1 would give you x back, yeah. So what it's saying is that if you ever plug in a bigger number, you always get the original number back. All right, so why does this not work? Why can you not find a single number that always spits out the original number back? Like, I agree that identity failed. We need to say why. Yeah. Good. Yeah. So actually, in this case, not infinite small numbers, but infinite bigger numbers, right? You can always find a bigger number. Yeah, infinite smaller one that would be like like if this was max, right? Then the identity would be some infinite smaller number. Yeah. So like if an identity exists, then this number must be greater than every real number. Yeah, so all identity means is it's some special number where if you add it to any other number, you always get, it doesn't change. So sometimes 0 is the thing, if it's addition. Sometimes it's 1, right? It depends on what the addition is. So in our max, or this is min, right? In our min world, right? This E number needs to be bigger than every single number, right? So like, and you see why that's not true, right? There is no such number. Right, maybe you can say like infinity, but that's not a number. Okay. So does that make sense? So what we know about real numbers is there is no biggest number, right? If there was an identity, that would be the identity. The biggest number would need to be the identity, but that's not a thing. All right, questions about that? You agree that there's no biggest number out there? You can always plus 1 to anything, right? So you can never get a biggest. All right, which one was this? This was C. All right, let's do the next one. All right, non-singular matrices. That's my set. My addition, right? My binary operation is matrix multiplication, and it's usual scalar multiplication. All right, so let's think about that one. Anyone see where that fails? Okay, so the set is called non-singular. Let's just call it n by n, for some n. It's matrix multiplication. That's the binary operator. And then our normal scalar multiplication is our scalar multiplication in R. So the normal, usual. All right, so which do we think fails? So it should be screaming at you. Commutative, good. Yeah, matrix multiplication is not commutative. Oops. Yeah, you can find ones that don't work. Right, there's one that doesn't work, and then so it never works. But notice that other ones are fine, right? That it is closed. Product of non-singular is always non-singular. It is associative. The identity is the identity matrix, and non-singular matrices have inverses. And it's and all the things in scalar multiplication works too, right? Scalar multiplication. Oh no, actually, what's a number? Yeah, why is it not closed under scalar multiplication? Can you see why? 0. Yeah. 0 times a is equal to 0 is singular. Right, so that one doesn't work. The distributivity is fine, scalar multiplication, all the rest are fine, but it's not closed under under the field, and it's not commutative. All right, questions on that one? That's right. Just solid one that didn't work. So that's good. So I would say to be more precise is to find an example. I mean, we know a lot of examples, so, or you can figure one out pretty quickly. So we won't do that one. But okay, so let's just do the next one. Diagonal matrices. Scalar multiplication or matrix multiplication. And scalar multiplication. Okay. What do we think about this one? Sure, let's review that. So what is diagonal? Okay, so if A is diagonal, if Aij is equal to 0 for I not equal to j. So that's what diagonal means. So the only things that are possibly not 0 are the things in the diagonal. So you can also think of it as both upper and lower. Well, think about matrix multiplication. It actually is commutative. And let's kind of understand why. What is matrix multiplication do? So if I have A times B, what are the entries Aij, Abij? Good, yeah, it's the diagonal elements that are multiplied. So you should know this sum formula. I keep on writing it for you because that'd be too hard to type. Yeah, so what are the entries that are 0? What is this equal to? Yeah, so look at the indices. Where is this only possibly not 0? Yeah, it's 0 when I is not equal to j. So it's only equal if it's like ai, right? Only non-zero if k is equal to only possibly non-zero if k is equal to I, right? And then this is only possibly 0, only non-zero if I is equal to j, right? So AB, I, and you can look at this in the picture. You have two matrices, is AII, BII, right? So for example, I have stuff over here. So the first entry is always just the product of the things in the diagonal, right? A, B, this is always AB. But if I flip the multiplication, I still get AB back, right? So this actually is commutative. Is it closed? Is diagonal times diagonal always diagonal? Yeah, I'm not going to magically get something non-zero in one of the upper or lower parts. It is associated with matrix multiplication. What's the identity? Identity matrix. Is that diagonal? Yes. I is diagonal. How about inverses? Good, yeah. Inverses are not guaranteed. And why is that? It's because the diagonal just means that these upper and lower triangle entries are zero. It says nothing about the diagonal entries. One of the diagonal entries could be zero. And why is that a big problem? What does a zero in the diagonal tell you? Good, it makes you a zero row. Yeah, could be singular. Another answer to that would be the determinant of a diagonal matrix is just take the product of the diagonal. And if one of them is zero, the determinant is zero. Good, good. So does this mean if I just added in non-singular diagonal matrices, would I get a vector space? Right, the only problem with this, if you look at the other side, right, it would be okay, right? So the only problem with this is inverses. If I just included non-singular diagonal, right, then I get inverses. Would it be a vector space? So what happens when I add non-singular? I get inverses, but I'm suddenly restricting myself, right, to non-singular. Yeah, so which fails if I add non-singular? So it's the one that failed for our other non-singular case, right? So it's not necessarily true just adding in some properties will fill in the blanks, right? Because once you add in some properties, you might take away from some other properties. Okay, so questions on that? Oh, if I add non-singular, then multiplying by zero would still give me a singular matrix. It's not closed under scalar because you can multiply by zero. Yeah. Yeah, zero is always a pesky one, right? I always think that's like the first one I like to check because, like, how does zero work in this world? But yeah, it is actually closed for just diagonal. The zero matrix is diagonal. Yeah. So it's literally just adding a property and taking away a property if you throw in the non-singular. All right, let's do, so the next one was diagonal matrices again, but this one was matrix addition. And usual scalar. All right, so now we're looking at just at a new binary operator. All right, so okay, same set, but we're doing a different binary operation. Okay, is it closed? If I do diagonal plus diagonal, will I get diagonal back? Yes. Is it commutative? Is matrix addition commutative? Yes. Is it associative? Yes. What's the identity in this world now? zero matrix, yeah. And what are the inverses? Remember, this is additive inverse, right? The negative matrix, yeah. A plus negative A is equal to 0. Yeah, remember, inverse always implies to the binary operation, right? Yeah, so there's no multiplicative inverses in this world. Is it closed? In scalar multiplication? Yeah, right? All you're doing, right, is when you do scalar multiplication, you're just multiplying every entry by alpha, right? And if everything else is 0, then you're not adding anything to that entry. It is distributive. That's what our usual scalar multiplication is distributive. Usual scalar multiplication is distributing scalars as well. Yeah, so it's actually everything is fine. So this is a vector space. Now, can you see compatible in field? It's damn. Sorry. This always happens at I don't know how to undo it. On the 8th. Oh, now it's good. All right. One in distributive, these. All right, so distributive in vectors means that I can distribute over the vector binary operator. Distributive in scalars means that I can distribute over the field operator. And compatibility means that if I have if I have two separate scalar multiplications, it's the same as doing the field multiplication and then scalar multiplication. Right. So, yeah. All right. So I have a question for you. So this world here, diagonal matrices with matrix addition. Can you think of another set that kind of is pretty much the same thing as this? Like, think about matrix, thinks about diagonal matrices, and think about how matrix addition works. Let's just kind of do an example. A, B, C, D. Can you think of another set that well, upper is a little bit different, right? Well, I think the upper triangular would still be okay. So would, yeah, I think all matrices would be fine here, right? I was thinking like, what would happen if I like took away these zeros? Right, these zeros don't really play a role, right? Because when I'm adding matrices, they're just pretty much disappearing, right? when I multiply any scalars, nothing happens to those zeros. So do you see that they're kind of like, I could do all of this just like this, right? All of the computations are just working on the diagonal entries. Do you see that? Like, yeah, so this is essentially like n by 1 matrices, right? These are just vectors. So upper and lower triangulars are a little bit different. I mean, we would have to add more to the dimension, right? So it's essentially like R4. So diagonal 4x4s are essentially just like 4-position vectors when I'm looking at matrix addition. So if you think about it too, the same thing would be true for 2x2s, right? All of these properties work if it's just normal matrices and matrix addition. Do you see that? Adding 2 2x2s together computatively is the same as adding 2 4x1 vectors, right? See that? Like if you do all your computations in 2x2s, the result would be the same as if you did your computations in 4x1s. Right? Does that make sense? All the scalar multiplications kind of like follow over all of the, let's just kind of like do an example like A, B, C, D plus X, Y, Z, W, A, B, C, D plus X, Y, Z, W. Do you see why like they're essentially the same? Yes, no? Yeah, so it's not true though if I add multiplication, right? Matrix multiplication is weird, right? And it doesn't really work the same way with vectors. There is no multiplication of vectors, or at least that's nice. Maybe it behaves the same way. But yeah, so it's generally kind of a fun fact that we can start with, it's true for all. If any square matrix is essentially the same as like just looking at our as vectors in the product of the dimensions, but it's kind of a fun, except for like diagonal, right? Because the kind of those zeros kind of go away. But nothing we'll kind of go into deeply about, but kind of keep that in mind, kind of for, as we're proceeding. It's like some of these operations that we do in some spaces look a lot like operations in other spaces. So adding 2 matrices, adding 2x2 matrices is pretty much the same thing as adding 2 4x1 vectors, right? The computations kind of carry over. But kind of interesting thing to think about. But only for addition, right? It would not work for multiplication. All right, so let's continue. Oh yeah, here's just a fun one. Okay, let's do the single set one with multiplication and scalar multiplication. All right, can someone say immediately which is the one that fails? So it's a single element set, just one. It's a multiplicative identity. And that's all I have. This should be a quick one. There's only one thing in there, right? Closed in which? Closed for scalar, yeah. Right, 2 times 1 is 2, not in the set, you're done. So this is in contrast with the one that we did last time. Right, so this is just to emphasize that this is sometimes called the trivial space with only one element. But you can't do that for every binary operation. Kind of what I want to take away from this is that you still need to care about what the scalar multiplication does. Just having the trivial space, meaning just the identity element, does not always give you a vector space. So multiplication is not as nice as addition is. Even though there's really nothing to look at, right? There's only one thing in there. For all intents and purposes, multiplication and addition should be the same, right? But scalar multiplication behaves differently in these separate binary operations. Okay, I just wanted to do that one. Since we're just a little low on time, I'll just kind of go through these a little quicker. One variable functions on the plane. So I mean, just any functions. So this is stuff that we did like in pre-calc. And the binary operation is composition. So can someone remind me what good, it's not commutative. So what does composition mean? It means that you take in the input yeah, so if I have like f of g of x, it's equal to plug in g of x, but good. It's just generally not true. They can't flip it. So one of my favorite examples of this is f of x is equal to sine and g of x is equal to x squared. Can someone say what f of g it would be? And then someone else say what g of f would be. Yeah, the first one is the x gets the square. And good. The second one is the sine gets the squared. That's my favorite one for doing composition. So yeah, so it's not commutative. Another answer would be it has no inverses don't exist. Can someone say why that's not true? So first of all, what is the, we'll start with that. What's the identity function for functions? So what is the function where you do like f of g of x, what's called e of x for a different letter? F of e of x is equal to f of x. And e of f of x is equal to f of x. Good, yeah, e of x is equal to x. It's the identity function. So why do functions why do not all functions have inverses? Which functions don't have inverses? Do you remember there's a couple ways you can phrase it. Going too far back? How about if I drew a picture? Could you tell if this has an inverse or not? Yeah, inverse meaning like, can I compose this picture that I drew with another function that gives me the identity back? Yeah, what is the flip? It's a flip over this line. Yeah. So the idea is that when you flip it, you don't get a function back. This is not a function. But horizontal line test would be a word that you may remember at one point. One-to-one is another word. Yeah, only one-to-one functions. Only one-to-one functions, or in other words, pass the horizontal line test. These are the only ones that have inverses. So end of the day, composition is not commutative. That's kind of the big one. But another answer would be functions, not all functions have inverses. So it's funny, this kind of looks a lot like matrix multiplication, because matrix multiplication can be viewed as functions as well. So kind of a similar kind of reason why it's not a vector space as well. All right. All right, I'll let you think about that. Think about that one. If I replace composition with addition, it works. So I'll let you do that one. But I want to talk about just quickly vectors on a plane. Yeah, that is true. Not all functions have inverses. And the ones that do have inverses are called one-to-one. We call them non-singular. So that's specifically to matrices, but in general, we call those things, they're not one-to-one. Some functions do have inverses, the ones that are one-to-one. And what is the inverse is based on the binary operation called composition. So that's why we call them inverses, right? I think a lot of pre-calc students, when they see inverse, they quickly do 1 over f of x, right? But we're not talking about multiplicative inverses. That would be true for multiplicative inverses, but not for compositional inverse. All right. Let's think about how vectors work on a plane. So, big thing I want to say is these are not coordinates. So I think one kind of assumption that you might want to make is that vectors, so vectors that we've been talking about are things like x, y, and one way to imagine these as vectors, not as coordinates, well, we want to talk about vectors as things that you can add together, things that you can multiply. There's no kind of natural way to talk about adding coordinates, right? It's not really a physical thing that you can add, right? What is 1, 2 plus 2, 4 equal? Well, that's not, I mean, those are just points on a plane, right? Those are actually physical points. How do you add points together? Well, you don't, right? So what we want to do is, how can we differentiate between something we call a vector, some things that we can add together, things that we can multiply, and how do we differentiate between just points? These are coordinates. So one kind of natural way to talk about vectors is, by some like kind of physical action. That's kind of like a natural way to talk about what vectors are. So here's kind of how I like to describe it. So let's say you're sitting on, everyone is sitting on a plane. Let's say, yeah, so we'll see how direction plays a role. So everyone's sitting on a plane and everyone jumps in a certain direction. So let's say I jump this way and I jump that far. Let's say, Sebastian, you jump this way, you jump that far. So, someone else jumps this far and someone else jumps that far. So this is an action that we all made, right? Well, let's say someone else was sitting here and they jumped the same way that I did, this way. And they jumped the same, at the same amount. Now, to an observer, like, would you agree that you know, these pair of people pretty much jumped in the same way, right? They both did the same thing, right? That would make sense, right? They just started in different places, but they did the same action. Would you agree with that? You know, they just started at different points. And maybe this person jumps this way. This person jumps this way. And they all did the same. These people all did the same action, right? So all these people did the same thing. Their jumping power was the same and they jumped in the same direction. Great. So we're going to call those, so if we're going to group these things based on actions, then all of these are the same action. So we're going to say that all these three things are the same vector. So we're going to call those things the same. All right, so that's how we're going to define vector, is that, all right, so vector will mean, we'll just call it jump some amount in some direction. So if everyone's jumping at different locations, jump the same way and by some amount, then instead of all of these vectors call it the same, that'd be hard to work with, right? If all of these things are the same, there should be a way to kind of universally describe this as one vector, right? We want to give a representative. We think of these are all the same people. These are all people, and we want to pick one of these vectors to be, you know, the representative president or whatever of all these vectors. So what is the nicest vector we can talk about? Yeah, so this is, all these people are jumping some direction northeast by some equal amount. So we're going to say, let's call all these vectors the same as this vector. This is the representative for this group of vectors. So when we talk about vectors, well, we could just say the one who starts at the origin, they speak for all vectors. So that's going to be our kind of our standard vector. Does that make sense? So if I talk about the red one, I'm also talking about all the other ones. So we're going to say starting at the origin and jumping a certain amount in a certain direction. That's how we're going to talk about vectors for the most part. All right. Almost done. We're pretty much done, but I just want to give you brief kind of description of addition and multiplication. So this is how we're going to find addition. Very naturally is if, let's say I jump this direction that amount, and then from this point, I jump this direction this amount. The net jump is what we're going to describe as the sum. So if this is the vector meaning jump this way for this far, and this means jump this way that far, it's the same as jumping this way for that amount, as if I were to kind of go diagonal. And why is it commutative is that if I reverse the order, I get a parallelogram. All right, so we're out of time, so I'll extend the homework because we're going to talk more about this, vectors on a plane. But so Monday, let's just do it for Wednesday. So we have class Monday, and then you can do everything except for maybe could even figure out this stuff. Questions 1 and 2, let's rely on vectors in the plane, but I wanted to save until now to do it. But I'll finish this talk about vectors in the plane. It's kind of more physical representation of vectors rather than like purely mathematical, abstract. So we'll do that on Monday. And let's just say try to get in by Wednesday. Only be 2 problems. Yeah, so we'll kind of give better words for that later. So yeah, by amount, we're meaning just distance traveled, right? I mean, and that's kind of a nice kind of standard physical description of it. And that's what magnitude means, it's length. Chapter of the final, it would be 3.1, and then whatever the syllabus is after that. So this is 3.1 right now. Let me start recording.